Welcome back to CS Connect series. This video will be about the cardinality of sets. This concept will be following after functions, sequences and summations video. Let's start with the cardinality of sets. The sets A and B have the same cardinality if and only if there is a one-to-one correspondence from A to B. So in order to understand this one-to-one correspondence, you need to watch functions video in Mathematics for Computer Science playlist. When A and B have the same cardinality, we can write it this way. So the number of elements in A will be equal to the number of elements in B. The size of set A is equal to the size of set B. But in the case of infinite sets, the definition of cardinality provides a relative measure of the sizes of two sets rather than a measure of the size of one particular set. Relative measure in the sense we can say that one set is less than or equal to the other set's cardinality. Only in terms of comparison, this particular relative measure can say which set has more number of elements and which set has less number of elements. If there is a one-to-one function from A to B, the cardinality of A is less than or the same as the cardinality of B. So it can be written in this way. You have the domain here and you have the codomain here. In one-to-one function, we have a mapping from domain to a value in the codomain, that is giving an exact mapping. There is no need that range should be equal to the codomain. We can have A, B, C here, 1, 2, 3 here. A and B can map to 1, C can map to 2. In this case, there is a possibility of the codomain to have more number of elements compared to the domain. So that's why they say when there is a one-to-one function from A to B, the cardinality of A will be less than or the same as cardinality of B. That is what is given by this notation. When set A cardinality is less than or equal to set B cardinality and A and B have different cardinality, the cardinality of A is less than cardinality of B. So what they are trying to say is lesser than or equal to will be turning as less than B. Now we'll get on to the countable sets concept. A one-to-one correspondence between Z plus and the set of odd positive integers. So this is positive integers and this is odd positive integers. So Z plus will have 1, 2, 3, 4, 5, 6, 7, 8, 9, it goes on. Set of odd positive integer has 1, 3, 5. Only the odd numbers are taken. A set that is either finite or has the same cardinality as the set of positive integers is called countable. A set that is not countable, we call them to be uncountable. When an infinite set S is countable, we denote the cardinality of S by this particular notation. This notation is actually called Aleph null. An infinite set is countable if and only if it is possible to list the elements of the set in a sequence indexed by the positive integer. In order to know what is a sequence, you have to watch sequences video under Mathematics for Computer Science playlist. What is the reason behind that? A one-to-one correspondence F from the set of positive integers to a set S can be expressed in terms of a sequence A1, A2 and AN, where A1 is equal to F of 1, A2 is equal to F of 2 and AN is equal to F of n. Now we will see some examples for countable set and uncountable set. Let's start with countable set. The set of all integers is countable. The set of positive rational numbers is countable. So let's take the rational numbers here. What are rational numbers? Anything in the form of p by q where q is not equal to 0. So here 1 by 1 is 1, 2 by 1 is 2. So this is 1, 2, 3, 4, 5. Which is expressed in the form of fractions divided by 1. When you get on to the fractional part, this 1 will be divided by 2. So every number will be divided by 2. In the next row, every number will be divided by 3. In the next row, every number will be divided by 4. In the next row, every number will be divided by 5. So if you keep on going for the subsequent rows, it will be divided by a particular number. Whenever a number p by q that is already listed, it is not listed again. Now let's take 1 divided by 1. 1 divided by 1 will give you 1. 2 divided by 2 will give you 1. So in both the case the value is same. So if we have circled 1 by 1, we would have not circled 2 by 2. Similarly, what is 2 by 1? It is equal to 2. What is 4 divided by 2? That is also equal to 2. Since we have circled 2 by 1, which gives a value of 2, we have not circled 4 by 2. The initial terms in the list of positive rational numbers we have constructed are 1, 1 by 2, 2, then we have 3. From there we go with 1 by 3, just go with the arrow mark. From there we go for 1 by 4. Then 2 by 3, then 3 by 2, then 4, then 5 and it comes to 1 by 5. Because all positive rational numbers are listed once, the set of positive rational numbers is countable. Now let's take the uncountable set example. The set of real numbers is an uncountable set. Suppose the set of real numbers is countable, then subset of all real numbers that fall between 0 and 1 should also be countable. So they are taking only one range between 0 and 1. Let's take the decimal representation of these real numbers. In between 0 and 1, what are the possibilities? We have 0.1, 0.2, 0.3, 0.4 till 0.9 we have in terms of one number after the decimal. But in general, the representation will be R1 is equal to 0.D11, D12, D13, D14. R1, R2, R3 are the set of real numbers between 0 and 1. Dij belongs to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, this particular set. What does it mean? If there is a number called D11, it can have any number from this particular set. Every real number has a unique decimal expansion is what they say. All the real numbers between 0 and 1 cannot be listed if we go in this aspect. It is quite difficult. Initially you can start with 0.1. Then 0.11 is also between 0 and 1. Then 0.111 can also be listed between 0 and 1. Do you know the length of this particular decimal representation? No. You know you have to pick numbers only from 0 to 9. But you don't know what will be the length after the decimal point. In that case, we can say that it is uncountable even between the range 0 and 1. But here we are proving it is quite difficult to count even between 0 and 1 because every real number is going to have a unique decimal expansion. If that is the case for 0 and 1, it can be extended to the complete set of real numbers. Any set with an uncountable subset is also uncountable. So what they are saying, the 0 and 1 range has been declared uncountable based on this particular representation. This is actually a subset of the real number. If subset itself is uncountable, then the superset will definitely be uncountable is what they say. Hence, the set of real numbers is uncountable. Cantor diagonalization argument. This is used to prove that the set of real numbers is not countable. So, this is what they say in terms of Cantor diagonalization argument. Now, let's go to the next concept. If A and B are countable sets, then A union B is also countable. In this, we have three cases to consider. The first case is A and B are both finite. A union B is also finite and countable. If A is infinite and B is finite, then we will have the union of A and B to be countably infinite. What about the third case? A and B are both countably infinite. So the union will also be countably infinite. So whatever cases apply to A and B individually, when they come under union, whichever has the higher domination should be taken. So among infinite and finite. Infinite has a higher domination. So we are bringing infinite here. Now both are countably infinite. So we are using the same terms for union operation also. We have a theorem here, Schroder-Bernstein Theorem. If A and B are sets with cardinality of A less than or equal to cardinality of B and cardinality of B less than or equal to cardinality of A. This is something like when A is a subset of B and B is a subset of A. What do we conclude in subset concept? A is equal to B. Similarly here, based on the cardinality, what they are concluding? The cardinality of set A will be equal to the cardinality of the set B. If there are one-to-one functions f from A to B and g function from B to A, then there is a one-to-one correspondence between A and B. Now we will see some examples regarding this particular theorem. Show that the cardinality of 0, 1 interval elements is equal to the cardinality of 0, 1 with 0 as open interval and 1 as closed interval. This means it does not include 0 and does not include 1. While this means 0 is not included but 1 is included. Finding a one-to-one function from open interval 0, 1 to 0, 1 with 1 as closed interval. We have to find from A to B now. We know 0, 1 in open interval is a subset to, that too a proper subset to 0, 1 with a closed interval. Now let's take real numbers here. Anything between 0 and 1. So let's take 0.2, 0.3 and 0.4 as the element. Now anything between 0 and 1 with 1 included here. So we will have the same set of elements here. Is this a proper subset? Yes. Because in this particular interval you have 1 here. If you have 1, definitely that has to be present in the range. But that one is not present here. You can definitely say this particular range is subset to, that to a proper subset to this particular range. So f of x is equal to x is a one-to-one function from this interval to this interval. Now we have to construct in the reverse side, B to A. Finding a one-to-one function from this closed interval of 1 to open interval of 0 and 1. Here g of x is given by x divided by 2. It is a one-to-one function and maps this particular function to 0, 1 by 2. So what they are saying is when the function is going to be x divided by 2. What is this 0, 1 with closed interval? 1 by 2 will give you 0.5. So can you place this inside this particular interval? Yes, you can place. So what they have done is they have found a function g of x is equal to x by 2 as a one-to-one function and they are mapping 0, 1 to 0, 1 by 2. So when you have 1 divided by 2, it gives 1 by 2. This mapping is done when you are taking this to be B to A part. Now this 0, 1 by 2, this is open and this is closed. This is a proper subset to 0, 1. 0 will be there, 1 by 2 will be there and 1 will be there. So let's take only 1 by 2. Regarding 0, 1, what are the possible values? We can have 1 by 4, 1 by 2, 1 by 3, etc. Now, is this a proper subset to this one? Yes, it is a proper subset. So, here the mapping goes from 0, 1 with the closed interval option to 0, 1 by 2 with the closed interval option under the function x by 2. And this particular range or the interval is a proper subset to 0, 1 in open interval. So, when x divided by 2 is given as the function, we know the maximum element in closed interval is 1. It should not exceed 1 in this particular interval. So, substitute that 1, you will have 1 by 2. That's why you are stopping this particular interval with 1 by 2. by finding one-to-one functions from open interval to one-side closed interval and from one-side closed interval to open interval. The Schroder-Bernstein Theorem tells us that the cardinality of both the sets will be equal to each other. Now the next concept will be uncomputable functions. A function is computable if there is a computer program in some programming language that finds the values of this function. If a function is not computable, then it is uncomputable. If you are not able to find a value, then it becomes uncomputable. To show that there are uncomputable functions, we need to establish two results. What are they? We have to show that the set of all computer programs in any particular programming language is countable. What is the other result? Show that there are uncountably many different functions from a particular countably infinite set to itself. So we have to show these two results in order to show that there are uncomputable functions. Now we will see a hypothesis called Continuum Hypothesis. It can be shown that the power set of Z plus, if you want to know the concept of power set, it will include the empty set, it will include the set itself completely, and it will contain all the subsets. That is called as power set. If you want to know about power set concepts, I would like you to watch sets video from the same playlist, Set Theory. The power set of Z plus and the set of real numbers R have the same cardinality. So they have given it in the form of notation. Power set is mentioned as P of some set. So P of Z plus cardinality is equal to R's cardinality, and that is equal to C. Actually this is not C, it's another symbol where this symbol denotes the cardinality of the set of real numbers. It is actually called lowercase fructure C or fructure C. It is not normal English alphabet C. The cardinality of a set is always less than the cardinality of its power set. If we take a set S, then this will be the cardinality notation. So this cardinality of set of positive integers is less than the power set of positive integers cardinality. Rewritten S as, so we saw a symbol cardinality of S is equated to aleph null symbol. So this aleph null symbol is what here we are comparing it to the cardinality of S, that is less than 2 power aleph null symbol. This will be the cardinality of the power set. So we are equating that to 2 power aleph null symbol. So let's take a set S. To denote the cardinality of the set, we are using the symbol. To denote the cardinality of the power set, we are using 2 power the cardinality of set S. So this is cardinality of set and this is the cardinality of power set. The cardinality of a set is always less than the cardinality of its power set. Hence, Z plus cardinality is less than power set of Z plus cardinality. This is again rewritten as aleph null less than 2 power aleph null, where aleph null will be the cardinality of the set and 2 power aleph null will be the cardinality of the power set. Using the notation 2 power cardinality of set to denote the cardinality of the power set of S. Now we are taking this particular equation. So instead of this particular power set of Z plus, we are going to use 2 power aleph null, and instead of the cardinality of R, we are going to use this fructure C symbol. So this particular equation is now expressed as 2 power aleph null is equal to fructure C. There is no cardinal number x between aleph null and fructure C. Now let's see the continuum hypothesis. The continuum hypothesis states that there is no set A such that aleph null, the cardinality of the set of positive integers, is less than cardinality of set A, and cardinality of set A is less than C, the cardinality of the set of real numbers. So they are saying that there is no set A such that both these conditions are there. The continuum hypothesis is still an open question and remains an area for active research. Let's get into the practice problems. Determine whether each of these sets is countable or uncountable. For those that are countably infinite, exhibit a one-to-one correspondence between the set of positive integers and that set. Let's start with the first one. All bit strings not containing the bit 0. The bit strings not containing 0 are just the bit strings containing all ones. So this set is lambda. Then we have one number of 1, two number of 1, three number of 1s. So we don't have any zeros here. Where lambda denotes the empty string, the string of length 0. Thus this set is countably infinite. You know this will go to a particular range, but you don't know where it will go and end. Where the correspondence matches the positive integer n with the string of n minus 1 number of ones. So when it is lambda, we say it is 0. When it is 1, we can map to 1. Similarly, when there comes a length n, there will be n minus 1 ones totally. When you find they are countably infinite, so this is countably infinite. So the correspondence matches the positive integer n, the set of positive integer, and the set itself. The set that is given in the question is this one. The first element is having no element. The second element is having one element. So that's why they say n minus 1 number of ones. Second subdivision. All positive rational numbers that cannot be written with denominators less than 4. The set of positive rational numbers is countable. We have seen that in an example. So here they are saying all positive rational numbers that cannot be written with denominators less than 4. So this is talking about a subset of set of positive rational numbers. So in that case we can say it is countable. To find a correspondence, omit fractions in the top 3 rows. Hope you remember this diagram. To find a correspondence, omit fractions in the top 3 rows. They have given cannot be written with denominators less than 4. So here it is denominator 1, denominator 2, denominator 3. These 3 rows will not be considered. After that it will be considered. That's why this particular part is a subset of the whole part they have given here. So it is countable only. Less than 4 means you will have only 1, 2, 3 here. Anything after 4 can be taken. So it is greater than or equal to 4 from here. Next subdivision. The real numbers not containing 0 in their decimal representation. This set is uncountable. We saw a set where Dij is equal to 0 to 9. Here they are saying the real numbers don't contain 0 alone, but still you have 1 to 9. When the real numbers were listed as an example of uncountable set, just excluding one number is not going to change that. This set is uncountable only. We'll go for D. The real numbers containing only a finite number of ones in their decimal representation. Finite number means only a certain number of ones are allowed. This set is also uncountable. It is talking only about the ones. You still have 0, 2, 3, 4, 5, 6, 7, 8, 9. So excluding this one digit is not going to make a big difference. That's why both the sets are given uncountable as the answer. Next problem. Give an example of two uncountable sets A and B such that A intersection B is finite, countably infinite, uncountable. Actually, we saw the explanation for A union B. Now the question is in the context of A intersection B. In each case, we can make the intersection what we want to be and then put additional elements into A and into B with no overlap to make them uncountable. So let's start with A. The simplest solution would be to make A intersection B is equal to 0. So both the sets should be uncountable, but Here A intersection B should be finite. For example, take A to be the interval 1, 2. So from 0, 1, 2, 3, 4, we are going to pick only 1, 2. You should not include 1 and not include 2. This will be A. And take B to be the interval 3, 4. Don't include 3, don't include 4. This will be B. What is the intersection of A and B? It is 0. What is A here? It is an uncountable set because we are referring to real numbers. And what about B? It is an uncountable set again. Remember, 0 to 1 itself is given as uncountable in the example explanation. So we are applying the similar explanation here. In order to make it finite, we are taking A intersection B to be 0. This is what they say here. We can make the intersection what we want to be. Finalize the intersection answer and then put additional elements into A and B to make them uncountable. So we have given two intervals for A and B for real numbers and ultimately made the intersection to be 0. Now what about countably infinite? Take the example from part A and adjoin the positive integers. The A intersection B part should be countably infinite. So let's take 1, 2 union positive integers. And along with B, you are going to have positive integers here. Now, what will be A intersection B? This will be completely ruled out and this will be completely ruled out. What is common between both of them? Z plus is common. So, Z plus will be the intersection point. A intersection B will be equal to Z plus. What is Z plus? It is countably infinite. So, this range itself is uncountable. This range itself is uncountable. But we are inserting an intersection point with countably infinite set which is Z plus. Now, A intersection B under C should be uncountable. Let's take 0, 1, 2, 3, 4. Excluding 1 and 3, this complete range will be A. What is B? Excluding 2 and 4, this complete range will be B. What is the intersection point here? The intersection point will be this particular part. We can take this to be something between 2 and 3. So this is A intersection B. Is it countable? No. So now we have A intersection B to be uncountable. Next problem. Show that positive integers into positive integers is countable by showing that the polynomial function. So the domain is Z plus into Z plus ordered pair and the codomain will be Z plus. F of m comma n is equal to m plus n minus 2 into m plus n minus 1 divided by 2 plus m is 1 to 1 and on 2. This is f of m comma n. Now we have to show that it is countable. How are we going to show? We have to say it is 1 to 1 as well as on 2. Let's start with m is equal to 1 and then we will start with n is equal to 1 to 7. What is 1 comma 1? So 1 plus 1 is 2, 2 minus 2 is 0. Here we have 1 plus 1, it is 2, 2 minus 1 is 1. 0 into something will give the complete set to be 0. M is 1. So 0 plus 1 will give you 1 here. What about f of 1 comma 2? Here we have 1 plus 2 is 3, 3 minus 2 is 1. 1 plus 2 is 3. 3 minus 1 is 2. What is 1 into 2? It is 2. 2 divided by 2 will go. Then plus m is again 1. What is the value? We have 2. Similarly, we have to compute for 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 6 and 1 comma 7. It has been already computed and then mentioned here. If you have doubts, you can compute it separately because this computation is not the main purpose of this particular problem. Now we will go for m is equal to 2, n is equal to 1 to 6. Then we will go for m is equal to 3, n is equal to 1 to 5. Then we will go for m is equal to 4, n is equal to 1 to 4. then m is equal to 5, n is equal to 1 to 3. M is equal to 6, n is equal to 1 to 2. Why have I reduced n's value when m keeps increasing is simple. You can calculate for any number of values, but to explain something I need only these many values. The function takes on successive values as m plus n increases. What is m plus n? It is 2. What is m plus n? It is 3. Here it is 4, 5, 6, 7, 8. What about m plus n here? It is 3, 4, 5, 6, 7, 8. Here it is 4, 5, 6, 7, 8. We have f of m comma n. So whatever is inside the brackets, just add those numbers, you will get m plus n. Similarly, you have 5, 6, 7, 8. Then you have 6, 7, 8. Then you have 7, 8. When m plus 1 is 2, you had the value 1. When m plus n is 3, you had 2. Then for the other case, you had 3. When m plus n is equal to 4, you had 4 here, you had 5 here, you had 6 here. So this will give 4, 5, 6. What pattern do you find here? The function takes on successive values as m plus n increases. When it keeps going on, the values keep increasing. Then go for this particular 5. 7, 8, 9, 10. So 7, 8, 9, 10. When m plus n is equal to 2, f of m comma n is equal to 1. When m plus n is equal to 3, it takes on the values 2 and 3 as we saw here. When m plus n is equal to 4, f of m comma n takes on the values 4, 5, 6. There are 3 values. When it goes for 5, we had 4 values. The range of values the function takes on for a fixed value of m plus n, say m plus n is equal to x, is x minus 2 into x minus 1 divided by 2 plus 1. What is this x minus 2 and x minus 1? Where did we get? Instead of m plus n, substituted by x. So you will have x minus 2 into x minus 1 divided by 2. Till x minus 2 into x minus 1 divided by 2 plus x minus 1. Since m can assume the values 1, 2, 3 up to x minus 1 under these conditions, and the first term in the formula is a fixed positive integer when m plus n is fixed. To show that this function is one-to-one and onto, show that the range of values for x plus 1 picks up precisely where the range of values for x left off. Let's take m plus n is equal to 2. What is the value? We have 1. When m plus n is equal to 3, it went to 2 and 3. When m plus n goes to the next value, from where it is starting? It is starting after this range. So till 4 we have 4, 5, 6. Now when m plus n is equal to 5, where does it start? 1 plus 4 is equal to 5. So it starts from 7. For one particular value, it is in 1. For another particular value, it is going for 2 and 3. For the next particular value, it is going for 4, 5, 6. From where it is starting? After 3 it is starting. The previous range, where did it start? It started after 1. When m plus n is equal to 5. Which number it has to start? It has to start after 6. So it is starting with 7 here. Here they are saying, in order to prove that this function is one-to-one and onto, we have to show that the range of values for x plus 1 picks up precisely where the range of values for x left off. So if you have a scale here, this is going to be x and this is going to be x plus 1. So if this is going to be, say for example, m plus 1 is equal to 4 and here this is m plus n is equal to 5. So m plus n equal to 4 and m plus n equal to 5. They are saying we have to prove that the range of values for this particular x plus 1 should pick up where the range of values x left off. So what are the values for 4 here? We had 4, 5, 6. So we had 4, 5, 6. Now what are the values for m plus n is equal to 5? We had 7, 8, 9, 10. Where did we pick up this value? We picked up from where x left off. X left off at 6 and we picked up for the next value. This is what we have to show. In order to show that, what they have given is f of x minus 1 comma 1 plus 1 is equal to f of 1 comma x. So to understand this, let's take a scale again. This is going to be x minus 1, this is 1 and this is x. This is going to be one range and this is going to be the other range. We have to find the values between this particular range, and wherever this range stops plus 1, this range should start. So if you have 4, 5, 6, this 6 should be taken. 6 plus 1 becomes 7 and this range is starting from here as per this example. This is what they say, f of x minus 1 comma 1. This range plus 1 should give you f of this particular range 1 comma x. So we will start with the left hand side and ultimately you have to end up with the right hand side. So here we have x minus 1 comma 1. So m is equal to x minus 1, n is equal to 1. So what is m plus n? X minus 1 plus 1, both will get cancelled and you will have only x. So this will be x minus 2 into x minus 1 divided by 2. And here we should have m. What is m? We have x minus 1 as m. So x minus 1 is placed as it is. This one is taken from the left hand side equation and placed as it is. Now you have to solve this. Let's go for x minus 2 into x minus 1. X into x is x square. Minus 2 into x will give you minus 2x. X into minus 1 as minus x. Minus 2 into minus 1 will give you 2. This will give you x square minus 2x minus x will give you minus 3x plus 2. Now this is just the numerator part. So along with this, x square minus 3x plus 2 divided by 2, you are going to add plus x minus 1 plus 1. So you can even remove the braces, it's just a set of addition only. Minus 1 and plus 1 will get cancelled. Now you have only x here. So this minus 1 and this plus 1 will get cancelled. Now we have to find LCM for this particular x. So this will become x square minus 3x plus 2. 2 into x will give you plus 2x divided by 2. Now x square will be placed as it is. Minus 3x plus 2x will give you minus x. This plus 2 will be as it is. The denominator 2 will also be as it is. So we have brought to this equation. Now we will split this as two terms. X square minus x divided by 2 plus 2 divided by 2. We are splitting into two parts because we need it in this particular format as given above. So now 2 by 2 will get cancelled and you will have 1. What about x square minus x? You can take x outside and this can be written as x minus 1 divided by 2 plus 1. Now this equation will be changed to this way. So we have got x into x minus 1. So here x is placed, here x minus 1 is placed, divided by 2, and we get this plus 1 by striking off 2 divided by 2. Now what is this particular equation? Let's take f of 1 comma x. So here m is equal to 1, n is equal to x. What is m plus n? It is 1 plus x. 1 plus x minus 2 will give x minus 1 in the numerator part, and 1 plus x minus 1 will take plus 1 and minus 1 and will give you ultimately just x. So this will be in the form of x minus 1 into x. So which form are we getting? When we expand f of 1 comma x, we will ultimately get this form. 1 comma x is equal to m plus n minus 2 into m plus n minus 1 divided by 2 plus 1. 1 is m here. 1 and minus 1 will get cancelled. What is 1 minus 2? It is minus 1. So we will have x minus 1 from this particular part and x from this particular part. The denominator by 2 will stay as it is and we will have plus 1 here. Now this is equivalent to f of 1 comma x. This is nothing but the right hand side. We have proved that LHS is equal to RHS. It means we have proved the range of values for x plus 1 picks up precisely where the range of values for x left off. The solution actually starts here. This is just an explanation of how we are bringing to f of x minus 1 comma 1 plus 1 is equal to f of 1 comma x. With this we are completing this video. I'll meet you in the next video. Thank you viewers.